Okay, this video is for the spreadsheet model we developed in class. We're going to develop a spreadsheet. We're going to assume the rocket goes straight up and that we're using the kerosene fuel, that 90% of the weight of the rocket is fuel. And I wanted to write a few equations before we jumped into the spreadsheet. So if we start with 500,000 kilograms at a mass flow rate, then mass flow rate times time is how much fuel we've burned up and shot out the back. So this is the mass as a function of time. Acceleration of gravity, and as we go up, of course, the gravity will decrease, but big G, big M over the distance from the center of the Earth squared. So I've got the radius of the Earth plus the height above the Earth. We've got a formula for the exit velocity, the thrust. Now for lift, since we're going straight up, we'll have a thrust pushing the rocket up, and we have to subtract off the weight of the rocket, which will be mass times gravity. And both mass and gravity are going to be a function of time and height above the Earth. Acceleration then is the net lift divided by the mass at that time. Velocity, we take the velocity at the beginning of the time step and add the acceleration times the time during the time step, and that's how we'll increment the velocity up. For height above the surface of the Earth, we'll take the height at the beginning of the time step plus the average velocity, the velocity at the beginning and the end over 2 multiplied by the time step. And so that's how we'll get to this. This is just such a mess. The spreadsheet, you can set this up yourself. I've got a lot of it set up just to speed things up. But the energy density of the fuel and the efficiency, I've got EF there. I should have put little e. And the mass flow rate, we're going to assume to be 2,500 kilograms per second blasting out the back. And we'll do the time in seconds, mass in kilograms. Gravity is in meters per second squared, exit velocity meters per second, thrust in newtons, lift in newtons, acceleration meters per second squared, velocity meters per second, and the height in meters. So for the time, we do 0 and 1, and then we block those two, and then we can copy it down. Now I'm just going to copy it down a little ways here. And, we got through the first 20 seconds. For the mass, we've got a formula. This is equal to 500,000 minus the mass flow rate. And we don't want that to index, so we have to push the F4 key. And then you see it brings in those dollar signs, and that tells Excel don't index times time. And we can just copy that down and see what's going to happen as we go through time here. And you can see the mass is going to decrease with time. But this allows us to change the mass flow rate up here, and the spreadsheet will just update. For gravity, see big G is 6.674 e to the minus 11. And the mass of the Earth is 5.9736 e to the 24. Divided by, we have to do a parenthesis, radius of the Earth is 6.371 e to the 6. Plus, and we're going to add the height above here, which we'll figure that out later, but we'll go ahead and pull that in, and we got to square it. So that gives us our formula for gravity. And right now the height terms are all 0, but we'll get that fixed here in a little bit. We can copy that now. The exit velocity is equal to 2 times, and once again we don't want to index on this, so we'll click the F4 key times, and the energy of the fuel, we don't want to index on that either, so we'll click the F4 key again, exit velocity of the fuel, meters per second. Thrust is equal to the mass flow rate, and we don't want to index on that, so we've got to hit the F4 times the exit velocity, and we can copy that down. Lift is equal to the thrust minus the mass times gravity. And once again, we can copy that down. For acceleration, we need to take the net lift force and divide by the acceleration, divide by the mass. You know, the F equals ma. So the acceleration, you know, I've messed it up here, equals the lift divided by the mass. And you can see that the acceleration will go up a little bit as the mass decreases. For a velocity, we're going to start with 0, and then in the second time step, we're going to assume it's equal to the acceleration. And here, this is key. You got to use this acceleration here. And we're going to assume that it's that acceleration through the first time step. This is an approximation times parenthesis, and the time step is this minus this. And we've got to add on the velocity at the beginning of the time step. And then we can copy this down. If you don't choose that acceleration that I showed us to choose there, this one, you'll end up with a circular argument when you do the height. The height, you know, we start at 0. And for this one, we're going to take, it's equal to the height at the beginning of the time step plus, and then we're going to take the average velocity, which is this, plus this, and we will divide by 2. The first time I'm going to go ahead and multiply by the time step, which is this minus this, and divide by 2. And we can go ahead and copy that down. And you notice as we copy it down, then everything updates, and the acceleration of gravity is decreasing a little bit as we go up in height, just like it should. From here, we can go ahead and copy this down, and you know, we need to go down until the mass is just 50 kilograms, and we can look up, you know, what is the speed and what is the height above the Earth at when we get down to 50 kilograms. But if you can get this developed, I think it'll help you on the last 2 homework problems.